Well, I don't know.
We're still here.
The signed homework yet, so.
This first chapter that we're studying is long, so. I won't
I
say
remember
more
last week, you just.
for a few more lectures, but then we'll see. All right.
The other person.
Are you gonna go over what it really means to have an eigenmode
The,
of a differential equation?
The
Because
reason.
it's sort of
that you
just
guys-
always
that
thrown
we call
around,
the gravity
that
fellows,
it's like
you guys would be
understood, but
cosmics.
intuitively doesn't really stick to what it actually means.
Yeah, in eigenmode, yeah, we're gonna go over some of that. I've decided to put off the eigenmode expansion to the end of the chapter.
There is no.
We'll cover that, but
Oh, shit.
we'll talk a little bit about it today.
The entire day, the half day that's remaining.
No, we were talking about, so I'm a Bradley fellow. And for, so there were prospects in your.
Because it's always been like a trend that's turned like, look, here it is,
So they
eigenmode.
wanted us to
You know how to do
convince
this,
them.
it's easy.
Well, That's, you know.
It's very
yeah,
important.
That's how I.
It's
how I
it's
know
very
for
important, and
roughly.
Oh.
get that it's some property of matrix.
No, we pull all the stuff.
It makes our life
Like,
easier, but it never really stuck in what it really is.
Well, so you're thinking of in terms of matrices, right?
They did, right?
But,
What is exactly Bradley Phillips?
It's just if you achieve high. It's just.
And the autofocus gives it a trippy effect.
If you did good in school,
Yeah.
that's all.
I need to.
Oh. Okay. It's like a form of fun.
When we brought them to the bar, it was good. Like, it was a short guy from Auburn, I think.
Add on.
That was funny. Or some, maybe it was one, I don't know.
I barely remember.
When I was a kid, I took
felt like
magnets to my chiropractor's secretary's monitor and broke the monitor, but it looked really cool.
Oh, yeah, you can do
The
that.
CRTs.
Joe Thomas and
Megan?
your guess is this, mine.
Were you that wasted?
Hmm?
Were you that wasted?
No, well, afterwards actually, but because they had to go home, so they did. So one guy had to fly at 6 a.m. So they all went by the earliest leaving. So they all left at
Not
around
progressing well, yeah?
like 9 o'clock.
Yeah, we left
Center.
like it was.
Maybe if you stand in front of it,
I
see
love that
autofocus will.
but that was for a different
Okay.
reason.
I thought we looked at.
It's good to focus. It's kind of focused on.
Yeah, we left really.
It's kind of focusing. Going in and out.
Which one?
They
It's not good.
they went to the Rona.
So, probably doesn't normally have the camera.
ROA.
Yeah, I've been there.
I could.
Yeah, there we go, yeah?
I could not
It's
have their
mechanical
skills there.
focusing. So it's analog, so it's
That
just
sounds fun.
slowly doing
I
until
wasn't
it
very
reaches-
good.
matches the point.
What?
I
And
was
if it
very
misses it, then
good.
it's sort of just stuck there.
Wait, so.
Very good, okay, let's see.
I still do, but I'm not good at it.
And yes.
I remember you had you guys were talking about the ham radio license. And I asked like, what's your license? And like the top one, what it's called. I was like, yeah.
Okay, good.
I'm not a real engineer. I just do that. I just do that. That's can't do all of you. We're in the same leadership group. We're good about it all the time.
I heard my name.
We're talking about. Hey. Talking about how she has a radio license and I don't.
You have what?
I forgot to update my radio license address.
Oh, amateur
I don't know if it still counts
Amateur.
anymore.
You get like a call sign with that or something, right?
Yeah. But I never really used it.
Call sign?
I forget.
I don't know, he said he had a.
I have a radio license,
ARL.
but I never updated the address when I moved, so I don't know if it's still valid or not. Cause they like give you like 3 months, but you must notify that you change your address or something.
Oh, yeah? All right, what do we got here? 6. Missing some people. I think a lot of people. On that line.
You like the blooming weather did?
What, the weather?
Yeah.
It's better than Michigan. I was in Michigan for a while,
So I've heard, yeah.
although I kind of miss it now. I like Michigan.
Like,
Not the snow, I had a good time up there.
So are you the type of person who explains Michigan as the glove,
Glove,
like
yeah,
I live
glove.
here?
well,
Yeah.
I love the right clothes.
It's gotta be the right hand, depending on how you turn it though, yeah. But yeah, I miss California a lot too.
Michigan looks like a glove, and they explain where they live.
I've never been to
based on
California, actually.
where.
California's awesome.
I've been told that, but I can't really, can't guess.
Out here, you have to drive, 45 minutes before you get to any other civilization.
They're building a metro. They're building a metro between the major cities of California,
Oh, really?
which would be like unheard of in the US. So if they actually pull it off without the car lobby trying to shut it down, then like having 3 super connected cities or 3 super cities connected would be a major economic boom.
Yeah.
Really has
In
been-
NorCal, so.
Because California's economy is bigger than some countries. So
There's a lot of,
they're trying to do the same in Texas with the
Bradford's up to New York.
Houston, San Antonio, Austin. There's some big oil lobbies that's trying to
It's just been like.
keep everybody in cars.
Reported in like.
So
Oh, yeah.
all, like the politician, and the politicians meet like
Yeah.
3 months a year, so they usually try to put some politics on useless issues.
I
Like
calculate. Actually.
Oh, yeah.
Actually, like, making your state better,
We get more
which
like
is completely passive.
Yeah.
It's like geometrical.
Very good.
I don't like those.
Hey, how's it going? Lamia, how are you? Good. Okay, now we filled the room, right? What do we got now? Okay, I think everybody's here. 14, 15, yep. Whoa. Missing one other guy I haven't seen yet, so he probably's gonna drop. Okay, so it's 4 o'clock. Let's get started. All right, so we did a lot of stuff last lecture, right? We verified some of the results that we derived for losses in waveguides. We had conductive losses that we applied to the metallic walls in the form of a sheet impedance. That model allowed us to calculate the power that was dissipated into the sheet impedance using an I squared R type of integral. And then we also incorporated lossy dielectrics by writing the propagation constant in a complex form, including the complex permittivity, epsilon RC, right? And then we got some formulas and we proved to ourselves that they were correct by doing some CST simulations and making sure we get the same results numerically, right? Which is somewhat backwards from what you normally do. You normally write a code and you use analytic results to validate it. But here we have a proven numerical code, CST, and we use that to check that we didn't make a mistake doing our derivations, and also to help us understand it, right? We want to understand the results that we derive, because at the end, it's an equation. There's a lot of investigation to do it and final results that you derive, right? You need to vary parameters, take limits, small argument, large argument, etc., until you understand what that equation is telling you about the physics, right? So this is one way to kind of get some insight, make sure that it makes sense to us, right? So we looked at that in terms of CST. We understood what it meant to calculate S21 from one port to another, and at least in the waveguide scenario, S21 was the ratio of the power at the output port with respect to that launched into the input port. And we calculated that using our analytic formulas and compared it to our numerical results. So that gives us confidence. It gives us some happiness about our result that we derived. Okay? Then we got to this point. So I have a lot of cool things to cover today, so I want to make sure that I kind of get to them, especially the end. But I want to make sure you understand everything. So slow me down if you're not understanding anything. It's better to launch into a discussion, right, about things you're not sure about than just not asking the question and me just going by it. All right? Okay, good. All right, so as I was saying before, this chapter is kind of a long chapter. There's a lot of different waveguides to study that have rectangular cross-section. So we're going to look at many different examples. We're going to continue now into, first topic we're going to study is how to expand fields in terms of these modes. So what have we found? We found the eigenmodes of the wave equation in the, and with the situation of the boundary conditions applied on the rectangular waveguide, right? So we solved the wave equation and we applied the boundary conditions of the rectangular waveguide. Okay, but then we derived some eigenmodes. Now we want to see how can we expand fields in terms of those eigenmodes. And it turns out the set that we have derived is not complete, right? Because we used the homogeneous wave equation to derive them, therefore they're divergence free, and therefore they can only expand fields away from the source, right? Because these modes are good for points not near the source, right? Or not on the source. So anywhere in the waveguide, you can expand whatever field you have there in terms of the modes that we've studied already. But let's see how you can couple, energy into the waveguide and find what this expansion looks like, right? So let's start first off with the homogeneous wave equation. So the electric field has to satisfy the inhomogeneous wave equation where the source is there now, right? So we're now including a source. We have the curl of E minus beta squared E is minus j omega mu j. The allowable modes can be found by solving the homogeneous counterpart, right? These are the eigenmodes of this differential equation. All right, so we have the curl of f sub m minus beta m squared f sub m, which is the same equation, except it's the homogeneous version away from source points, right? All right, the eigenfunctions that we're going to derive, we're going to force them to be orthonormal and satisfy the same boundary conditions as the original electric field, right? As E. What that means is, if I take the functional inner product of Fm conjugate dotted with Fn, and I integrate over some volume, then I should get a delta function, orthonormal. Orthogonal means that you get a zero result if m is not equal to n, right? Orthonormal means that you get a 1 if they are equal to. M is equal to n. Okay, so here, check this out. If I have a vector, A, and a normal vector, right? So let's say AX, X hat, AY, Y hat, AZ, Z hat. And I have another vector B, which is BX, X hat, BY, Y hat, plus BZ, Z hat, right? What does it mean if I do A dotted with B? Whoops. And I get a zero result. They're orthogonal, right? That means these two vectors are orthogonal. Now, if I write out what this dot product looks like, it's AX, BX plus AY, BY plus AZ, BZ, right? And that has to equal to 0. If that's true, then A is orthogonal to B. Now, let's say I increase the dimension of the space to 4 dimensions, right? Then what do I get? What is the orthogonality of a 4-dimensional vector? It's going to be the sum of AI, BI equals to 0, right? Yes. And I goes from, let's say 1 up to the dimension of the vector. So if we make it 3, then this is exactly the same as this, right? Okay, good. Now, what happens if I make it 4? Whoops. Can I undo what I did there? There's no undo. All right, so what happens if I make it 4? 0, right? If this is 4 now, then a 4-dimensional vector is orthogonal if it satisfies this equation, right? All right. let's say, and what am I doing? I'm multiplying these ordinate A and B at the same components, right?
There's still the one thing.
It's a 4 by 4, or it's a 4-dimensional vector, A is, and a 4-dimensional vector B.
Yeah, but it's still rank 1 tensor.
Sure. Yeah, it's a vector, so you can think of it as a rank 1. Okay. What if I make this 10-dimensional vector? Still this equation satisfies, right? All right. What if I now say that this is an infinite dimensional vector, and then I have to change the summation to an integration, and I have A as a function of x, B as a function of x, 0. What is this? This is the same exact thing, because what am I doing? Oh, I'm missing the dx. Hold on a second. Dx, right? What does this mean? This means that at every point x, I have some graph A of x, and then some other graph B of x. At every x, right, x sub I, for example, I'm going to multiply these two functions now. These are functions now. A function, what I'm trying to draw the analogy is, if you think of a function as an infinite dimensional vector, because this is a real number, right, real axis, a function of a real variable, I can evaluate that at any point. Okay, so I multiply A and B at a given x, and then I add it to the next AI and BI at the next given x through the process of integration, yeah? Now, that's exactly the same as this, right? If I think of a function as an infinite dimensional vector. So if it's true that A dotted with B is equal to 0 by multiplying the functions at a given coordinate or ordinate, or even at a given x, right? A given ordinate or a given component. But if I make the analogy, then I'm multiplying similar parts of A and B and adding them all up, right? Same thing here. If I get a result of 0, then those two functions are orthogonal. All right? So they're like infinite dimensional vectors, but they're orthogonal if you integrate them against, if you integrate one function against another and you get a 0 result, then those two functions are orthogonal. And what this is telling us here is that if m is not equal to n, then you get a result of 0. And if m equals to n, then you get a result of 1. That's what delta mn means. Okay, so ortho means this part, right? And then this could be any value. But orthonormal means this is 0 and this is 1. And then your conjugate you need because these are complex valued. All right? Okay, good. So now we've defined the properties of our eigenfunctions that we want and the wave equation of which they must satisfy. All right? So that gives us a vehicle to derive them. What we have to do is solve this wave equation here, this homogeneous wave equation, and ensure that this property holds by proper normalization. Then we'll have the FMs, right? All right, good. So that means we have a way to calculate FM. And now we can expand our electric field. They satisfy the same boundary conditions, right? These modes. So we can expand our electric field as a weighted superposition of eigenfunctions, an eigenfunction expansion. All right? You can think of these as the waveguide modes we've been talking about, Te to Z and Te to Z and Tm to Z. With these unknown coefficients, Am are complex numbers.
What was John calling on?
Yeah, this is a very general framework here, right? So these can be whatever, as long as they satisfy this differential equation. Remember, when you apply these boundary conditions, that's when you specialize the results of that differential equation, which are in general sines and cosines if we're talking about time harmonics, which we are in this case, or exponentials in rectangular coordinates. Then once you apply the boundary conditions is when you get the unique solution. Problem specific. Okay, good. So you can expand your electric field in terms of these eigenfunctions and what's called an eigenfunction expansion. How does that help us? Well, let's plug this electric field now back into the original inhomogeneous differential equation, which has a source on the right-hand side. Curl of the curl of E minus beta squared E is equal to minus j omega mu j. Let's substitute in for E. E now goes here and here. We get the sum of AN into FM, right? So here's the sum of AM, and here's our FM for the first E, and then minus beta squared E, we left that like that, right? don't know why I did that. That must be a typo. Let me see. Curl of the curl of M. Yeah, okay. Make this change in your notes, yeah? So this one should also be minus beta squared times the sum of AM, FM. And all that means is that we have to do this, right? And so the best way to do this, sorry, is this and change this to an FM. That should work, yeah? Because we factored out the sum of AMs and E became, yeah, good. All right, now we know that these FMs, satisfy this differential equation. So that means that the curl of FM is equal to beta squared FM from this equation here, right? And therefore, we can replace this curl of the curl of FM with beta m squared FM. Yeah?
So if the curl FM is equal to 0,
So here, let me,
we have 0 equals to
Let's-
some current.
let's start here, yeah? So the curl of, and then E is going to be from here, the sum, M, alpha M, FM, yeah? Minus beta squared, sum, oh my gosh, the sum, M, alpha M, FM, right? That's equal to minus j omega mu j. Good. Now we can factor out the summation in the alpha M and you get this expression, yeah? If you correct it like this, FM. Yeah? Okay, now we know that we have the curl of FM here, but we know that from this equation, the curl of FM is equal to beta squared FM, right?
Yeah.
So, or this. So that means we can replace all of this with beta squared FM. And that's all we've done here, right? So curl of FM became beta squared times FM. And then we factored out this FM that was here. So we end up with the sum of AM, beta m squared minus beta squared into FM. Yeah? Okay? And that's equal to minus j omega mu j. Very nice. Now, because these eigenfunctions were chosen to be orthogonal, right? Now what we can do is we can integrate both sides of this expression. Let me carry out the steps. Integrate both sides of this expression against Fn, right? So let's do that. So I'm going to say the integration over the volume of the summation of m, alpha m, beta m squared minus beta squared, Fm, and then we're going to dot that with Fn conjugate and dV. And do the same thing on the other side. Volume minus j omega mu j dotted with Fn conjugate dV. Yeah? So all I did was multiply or integrate both sides, take the dot product of Fn conjugate with both sides and integrate. And now, owing to the orthogonality, all this stuff is constants. They come out, right? Then I have the integration over the volume of Fm dot with Fn conjugate. We know that that's equal to delta Mn by construction. So, and then on the right-hand side, so on the left-hand side, this whole thing, so I'm going to continue this down here. This whole thing becomes the sum over M, alpha M, beta squared minus beta, or beta M squared minus beta into delta Mn, right? Delta Mn means I can just change all the n's to m's. Okay, great. And because all the other m's in this expansion, this summation, this is a summation over m, right? But only one of them is non-zero. You get 1 when m is equal to n and 0 for every other term, right, in the summation. So this summation breaks down into one single value. So you just get 1 there. So here, this is equal to alpha m beta m squared minus beta squared, right? Everybody good? Questions? Ask questions.
So where do we get the Fn conjugate on the right side when we're integrating?
What do you mean, here? So I take this expression, What's that?
Second row, we have the FN conjugate, so.
Here. This one?
Yeah.
So what I do is I take this expression, whatever I do to one side of an equality, I got to do to the other side. So I take the dot product with Fn conjugate both sides. Then I integrate both sides against the volume, dV. And that allows me to use this orthogonality relationship.
Doesn't matter which one you make a conjugate, as long as the function is conjugated.
Yes, that's correct. Okay, so now this is equal to this right-hand side, right? So I'm going to just say this comes down. Sorry, I'm kind of making this all sloppy as I'm drawing it. I should probably have a blank slide, right? Or for all these derivations. But this expression here comes down to the right. So now I can solve for F alpha m. I just divide both sides by beta m squared minus beta squared. And that's how I got this. So now we can calculate the coefficients of the expansion. How do we do that? The coefficients are proportional. We'll look at this on the next slide. To the inner product. So this bracket notation means this, right? So it means, let me write it here, bracket of, let's call it A and B. These are vectors, is equal to the integration over the volume of A dotted with B dV. All right? It's called the functional inner product. Yes?
So how come it changed from a FN to a FM in the inner product?
Good, good. Yeah. So it doesn't matter at this point, right? M is equal to N.
Okay.
So you can call it M or you can call it N. Yeah. So I mean, when this dot product here was taken, this is only valid when M equals to N. So I can either call them both M or call them both N, right?
Is this bracket related to the Cauchy integral, or is that just a coincidental similar notation?
No, I would not say that this is a Cauchy integral.
Because I've seen circle parentheses equal to that integral, with brackets is some other integral, so it's.
Yeah, Cauchy integral is like a path integral in a complex plane, right? So I wouldn't say that. Okay, so here's the electric field now, right? We found what alpha is. We can plug that in here, and this is what this expression is. So here's all the alphas. Here's the FM from here, and then all this is alpha, right? Cool. So that means that we can expand. We can expand our electric field in terms of these eigenfunctions Fm with these coefficients. So let's understand what these coefficients tell us about exciting waveguide modes, yeah? So there are a couple of different ways to excite modes in waveguides. One of them is to place a pin or a coaxial cable, like a monopole or some kind of filament of current into the waveguide at a quarter wavelength away from the back, right? I don't know if you can see that, but this says lambda, this thing right here says lambda g divided by 4. All right, why is that? Because, so this is let's see, here's another picture of it. Here's a coaxial cable coming up, right? The center pin of a coaxial cable. It is lambda by 4, this distance here is lambda g by 4. Why is that? So, yeah, you can think of it that way. So what it means is the radiation from this pin or this probe is going to radiate in both directions, right? Now, when it radiates to this shorting, to the shorted back wall, it's going to incur 90 degrees of phase delay because of the lambda g by 4. That means 90 degrees. Then it's going to reflect off of a perfect electric conducting wall where it picks up a minus sign, which is another 180 degrees of phase. Then it's going to go back to this direction and pick up another 90 degrees. So after all of that, you get 360 degrees. You're back in phase with the radiation that goes in the forward direction, yeah? Okay, so that's one way to do it. And there's another way if you put a loop like this shorted to the back wall so that you can couple to the magnetic field in the mode. So this is the broad wall B, right? So we're looking, so let me draw it. So here's the rectangular waveguide, right? Goes off like that. Here is X, this is A. Here is Y, this is B. So what we're looking at here is the wall B, right? So here's B. So we're kind of looking at it from here, placing a probe like that, right? And when we're looking at this cross section, we're looking at it from above as well, or from the side. So here's A, here's B. So you get both cross sections here, right? Here's A, here's, I don't know if you guys can see that. Can you see it? This is A and this is B. So this is the X direction, this is the Y direction. The loop comes into the middle of the waveguide and then loops back and shorts itself, the center pin back onto the waveguide wall. And here we have A and B. So this just comes in from the center of the top wall, lambda by 4 from the back wall. All right, good. Okay, so if we want to excite a certain mode, FM, to be strongly excited, we need this functional inner product to be large, right? Because the coefficient's dependent on that functional inner product. Therefore, we want the J, let's think of J as a filament of current, right? A linear line current that represents this center conductor of a coaxial cable. We want to place that J where we maximize the coupling or the functional inner product with the mode of interest. So if it's a TE10 mode, let me do that real quick. Where is the modal plots that we had derived before? Here. Where should I put the probe if I want to excite the TE10 mode? Right here, right? Because FM conjugate and J is a filament of current, a line current, right? And I want the functional inner product to be strongest here. That means that I want to place this where the field is the strongest and in the same direction as it's, right? They're vector dot products. If I place the probe here, what do I get? Nothing, right? But then I'd excite this mode. All right. How do I excite TE20?
Or we can have either a loop maybe.
You can put it on the maximum.
Yeah, so you have one this way and another one that way, right? So you can do it that way. You can probably use a loop too to couple to the magnetic field. So that's an idea of how to couple to these modes. All right. Now, that's one thing, right? First off, the current probe should be located where the field is the strongest. Another thing is this denominator. We want the resonant frequency of the mode. We want to operate at a frequency. Beta is our choice, right? Beta M is the mode, right? So we want to choose beta. We want to operate at a frequency where this nearly goes to 0 to have strong excitation, right? Divided by 0 is infinite. So we want to operate the frequency near the resonant frequency of the mode. If the operating frequency of the source is close to the resonant frequency of the mode, that mode is strongly coupled, all right?
So if you don't have the right matching with the right node, if you have beta and minus beta close to each other, you're still going to have a strong excitation.
Both of them count, right? Both of them contribute. Okay, good. All right. That's all I'm going to say about that for now. We'll do some problem. Yes.
So in general, are you exciting every mode all at once? Like if you excite TE10, you're going to excite TE30 at the very least, right?
Maybe not, right? So let's go. Remember, this depends on that functional inner product where I place that current. If I excite TE10 here, it depends on 30. Yeah. Okay. You will, right? You'll excite 30 as well. But the denominator won't be as strong because 30 has a higher resonant frequency. So you have two knobs to turn, the operating frequency and where I place that probe, right?
So access a filter.
It can, yeah. All right, so we'll get more into how to expand fields in terms of those modes. We have to derive those modes, orthogonal versions of them later on. Okay, let's look at rectangular resonant cavities now, all right? So before we studied this waveguide, which was unbounded in the z direction, and we had traveling wave solutions along the axis of symmetry, which is the z-axis. Now we bound the waveguide also in the z direction, leading to standing waves in all three directions. This forms what's called a resonant cavity. And resonant cavities are very useful to do, measurements of dielectric materials and the permittivity of them using cavity perturbation methods and things like that. And also for sources, right? If you want a high Q source, this is a good way to do that. We may reuse the same electric vector potential as we did for the rectangular waveguide, all right? Except now we are going to also bound it in the axial direction, forming standing waves. So before, we derived what the TE to Z modes look like in the X and Y direction. They were this, right? We applied those boundary conditions already, and we determined that this is the modal distribution for the distribution for the electric vector potential. But now, and we used to have e to the minus jkz here. But now we're going to change that to C3 cosine beta z plus D3 sine beta z and apply this new boundary condition on the front and back wall. This boundary condition at z equal to 0 and z equal to c. Now we have an extra parameter c, and z equal to 0 this should be C as well. Okay, make that correction. So I got two corrections to make. This one should be C. Okay, good. It should be equal to 0, right? So that should be easy to do. Let's do that. So we calculate the X component electric field using the same formulas as we did before, and we apply the boundary conditions. So here we have EX, and we calculate EX from FZ, but now we have to differentiate. This one doesn't change, right? Except for this used to be e to the minus jkz, but now it's C3 cosine plus D3 sine, all right? And we have to evaluate this at z equal to 0. If we do that, then cosine of 0 goes to 1, and sine of 0 goes to 0. But this whole expression has to equal to 0, and it can only equal to 0 if C3 is equal to 0. So we conclude that C3 must be equal to 0. All right, let's apply the other boundary condition now at z equal to c. And if we do that, we already know that C3 is equal to 0, so this term is gone. So we just have D3 sine of beta z into c. But in order for this to equal to 0, the sine function has to be 0. So then we conclude that beta z must be p pi divided by c, where c can be 1, 2, or 3, right? Good. All right. So then we can calculate what all the field components are for the cavity. Ex, Ey, Hx, Hy, and Hz. And Ez is equal to 0 because we're calculating the Te to Z mode, the Te to Z resonant cavity mode first. All right? Okay, very good. So let's clear that. All right. Let's look at the separation equation now. Beta x squared plus beta y squared plus beta z squared has to be equal to m pi over a squared. We found that eigenvalue when we did the rectangular waveguide solution. N pi over b also came from the rectangular waveguide solution. Now we have beta z as, instead of a continuous value for propagation constant down the direction of propagation, we now have p pi by c squared, right? Because it's standing wave in that direction too now. Good. Well, that we can call beta resonant. And we can expand beta squared as omega squared mu epsilon. And then we know omega is 2 pi f, right? Now we can calculate what a resonant frequency of the MNP mode. There are 3 indices now, the MNP resonant mode for the TE type modes, right? So 1 over 2 pi squared of mu epsilon, then we have the square root of these 3. And these are the range of indices that are allowed. M equal to n equal to 0 gives you a trivial solution. It gives you a 0 field, right? So you exclude that one. All right, if you have this condition, if C is less than A, which is less than B, then the lowest order mode is the TE101 mode. Now this is the dominant mode, yes?
P can't go from 0, start from 0 either.
P can't start from 0. Let's see. Probably because it is a sine function. It can, but it just goes to 0 as well, right? Let's see. Yeah. So if we're talking about EX here, or even EY, it's sine of 0. If you plug in P equal to 0, then that makes EY go to 0 and EX go to 0. So that's a trivial solution as well. So they just exclude that. The ones that give you 0 field, they just exclude them, yeah? All right. So, good. So this is the resonant frequency of the lowest order mode. How do you tune the resonant frequency of your source? If you want to make a source, you have a coaxial cable that might have some, wider bandwidth than you want. You want a narrow source. Then you can feed that into a cavity and increase the Q, right? So how do you tune the resonant frequency of your cavity? Mu or epsilon, fill it with a different permittivity, or change the dimensions. A or B, right? Good. Now the quality factor of these waveguide cavity resonators are very high, right? It's a very high quality resonance because there's not very much loss, right? So Q is equal to omega times the stored energy divided by dissipated energy. We know that, right? Omega times the total stored energy, omega or WT, divided by the dissipated power, which is into the loss of the waveguide walls or in the lossy dielectric that you put within the waveguide. The total stored energy is electric and magnetic. You add them both. And since they're the same, in this case, it's either 2 times the electric or I'm missing a 2 here, 2 times the magnetic. All right? Okay, good. So the numerator of this is a volumetric integral, right? the energy stored is integration over the volume. It's proportional to the volume. The denominator is an integration over the surface area of the waveguide because that's where the loss is. So it's proportional to the surface area, right? So the Q can be increased by increasing the size of the resonator. Okay, good. All right, so still, so let's calculate what this Q is. We can get a closed form expression for the Q of these resonators. So we're gonna do the same thing we did with the waveguide. First thing is, you calculate the stored energy, right? The numerator. So W total is 2 times the electric energy, which is 2 times epsilon over 4 times the volume integral of magnitude E squared, dV, which is D dotted with E, right? Okay, and if you plug in the distribution that we have for the electric field here, for the dominant mode, we're talking about the 101 mode, then we can integrate that. We integrate it here, and we end up with this expression here, okay? Very nice. Now we have to find the denominator, which is the total dissipated power. Same approach as the conductor loss, PD in a waveguide, except now we have a contribution from the front and back walls. So P dissipated is the integration of I squared R, right? 1/2 I squared R. Well, here's R, here's I square, in a sense, right? It's a field analog of that. We get 2 of these because the bottom and the top wall are the same result. Plus, we get 2 of these from the left and right walls, which are the same. Plus, we get 2 of these, which is the front and back wall. So this is bottom current, left current, and front current. That comes out to the loss in the bottom, the loss in the left, and the loss in the front, because this 2 here cancels all of those 2's. From the 1/2 integration of RS into J dotted with J conjugate.
Dissipated is different than dispersed.
Yes, yes, dissipated means that it's, in this context, means that it is converted into heat. All right, so what is JB, JL, and JF? Well, that's N cross H at Y equal to 0, or X equal to 0, or Z equal to C, right? And we know how to calculate those. We take our expressions for the magnetic field, we specialize them to the 101 mode, and then we evaluate them at Y equal to 0 after we take the cross product, right? And we have all those expressions on the previous slide, right? We have all the magnetic fields. Here, we have HX, HZ, and HY. Okay, good. So you get these field components, right? Great. Now we have to integrate them. And if you do that, then you get the following values here by integration, right? Okay, great. Now, the power dissipated, the total power dissipated comes from adding these 3. Remember, we had that here. Power dissipated is addition of these 3 contributions, and we get the following expressions, all right? Okay, now we have WE and we have power dissipated. We can form the ratio and we can get this closed form expression for the Q of this rectangular resonant cavity, right? Okay, so we did a lot of derivations again, and we ended up with a result. Let's understand this result or explore it. So this is the Q of the cavity, right? Let's check if these expressions are meaningful. So here's a design example. Yeah, okay. So let's look at this design example. So here is CST Microwave Studio, and what we're going to do is we're going to set up a simulation for one of these lossy resonant cavities that are made out of a rectangular waveguide, and we're going to numerically calculate what the resonant frequencies of the modes are and their Q in CST. So what you can do in CST is you can draw the dielectric inside, and you can say the exterior material, the exterior volume, the medium that you're placed in is a metallic conductor of copper with loss, right? Normally you would draw a waveguide in free space and you would draw the metallic conductor, right? But then you're assuming that you're embedded in free space. You can also use CST to embed yourself in an infinite lossy metal, and you can define like a cutout of that metal as a vacuum. Yes.
So what do you use CST and not HFS?
Just what I grew up on, right? CST I think is a lot easier myself, but you can become proficient in either. As a matter of fact, I know how to use all the tools, but if I need to do something really quick, I always use CST. It's easier to set up, I think. Yeah. Okay, great. So that's what this means. This is background properties. And I've set the background medium, the homogeneous medium, as a lossy metal of copper. All right, so here's the medium, the background properties of the medium, which you probably can't see it very well, but here's the conductivity, which is 5.7 times 10 to the 7, or 5.8 times 10 to the 7, which is copper. So it's a lossy metal, and I cut out of that metal this air box, this cube here. This cube has dimensions A equal to 2.286, B equal to 1.016, and C equal to A. So it's a cavity resonator with the length equal to the width, so it has a square bottom. And it's a WR, I think WR90. It's an X-band waveguide, the same waveguide we've been using in all these examples.
I have a question.
Filled with air. Yes.
The cavity resonator, does it matter what we excite it with? Can it always produce this high Q tone? Or will it convert our signal source into the resonant tone?
So we haven't talked about the excitation problem, right? What we're going to derive here is unloaded Q. This is a Q that incorporates the loss of the resonator itself. When you couple to it, then you have sort of this kind of external Q or a loaded Q if you put a load on it, where it'll change this, right? It'll have its own losses that'll contribute.
You have to also specify a specific source to get the high Q.
Yeah, I mean, you still have to couple into it, right? And couple out of it if you want it to be a resonator or source. Okay, good. So, all right. So square base, rectangular cross section. It's constructed, right? Constructed from X-band copper waveguide. For the dominant TE101 mode, determine the Q of the cavity, assume free space medium inside of the cavity. So I've drawn this free space medium inside of infinite copper medium. And we calculate first with the formulas that we derived what the resonant frequency should be for the 101 mode. So the pi over b, n pi over b disappeared because it's 0, right? 101. And we just have these two. We get square root of 2 over 2a square root of mu epsilon. If we plug in what the A is and we do some more gymnastics here with this equation, we get 9.28 gigahertz. Yeah? All right. We can calculate the sheet resistance to account for the loss. We know sigma for the copper, 5.7 times 10 to the 7. It should be 5.8 times 10 to the 7. And we get this, 0.0254 ohms, yeah? Then we can calculate the Q using the formula we derived. The Q of the resonator is only dependent on the loss, the sheet resistance, and the dimensions of the cavity. These are all dimensions, A, B, and C, right? Okay. If you do that, you get 7757.9 for the Q. All right. Then we run the simulation. Here what we're running is called an eigenmode solver in CST, meaning that there's no source, right? We're just looking for the eigenmodes of the geometry that we've set up, which is a rectangular cavity made of copper with free space inside. We run the eigenmode simulation without defining a source, right? And what it does is it solves the homogeneous wave equation, right? It finds at a given frequency what the resonant modes are. So it'll find the resonant frequencies of each of the modes. And it found 3 modes here because I only told it to look for modes between 5 and 15 gigahertz. The first mode it found was a resonant frequency of 9.2726, which is very close to what we calculated, right? So that's good. And then the Q of that mode, which is the first mode, it's a dominant mode, 7838, which is close to what we calculated. Very nice. All right.
Here, instead of a rectangle, we only have a one-dimensional mode instead of M and P or whatever.
Yeah, we'll study that in 2 chapters from now, the spherical cavity. Okay, what does it look like, right? What's going on inside of the cavity? So let's calculate the mode of profile. We derived the field expressions for these. Here's EY101, EY101 time harmonic is this expression, right? The term that depended on Y dropped out because we have a 0 here, and we have the mode indices are 1 and 1 here for the X and Z direction, all right? To find the time dependence, if we want to go back to time domain, then we multiply by e to the j omega t and take the real part, right? Now, because this is a standing wave cavity, then we don't get a function of the form f of x minus vt, right? So it's not a wave, it's a standing wave. That means it's e to the j omega t. All this is real, is what I'm saying, right? None of this is complex. These are not exponentials. All this is real valued, so it comes out. And we just take the real part of e to the j omega t. If one of these were an exponential, then it would combine with this and we take the real part and their argument would be omega t minus beta x. And then that would be a traveling wave. But this is a standing wave. All these are standing waves. Anyway, you get cosine of omega t here, right? So now I can change omega t from 0 to 360 and I can get these plots here. Let's look at these plots. Okay, so here's the magnetic field. So the magnetic field, we have hx and hz. We know the electric field is te to y, or sorry, te to z. These are te to z modes, te to z modes. So the electric field is transverse to the z direction, which means it's always in the xy plane. And in this case, because we have the the zero modal index for the y direction, it does not vary in y, right? There's no y dependence in the electric field, the y component. So this is purely it varies in x only. It's a y polarized electric field and it has no z components. All right? So this entire vector field in this plot are all vectors pointing vertical. And they vary in the x direction sinusoidally, right? That means that it's 0 at this end and 0 at this end and maximum in the middle, like this, right? Okay? And it varies sinusoidally in the z direction. So at x equal to 0, you get 0 here. At x equal to a over 2, you get a maximum. And at x equal to 0, or x equal to a, you get a 0 again. So you get this in the x direction. And in the z direction, you get the same thing. It's sinusoidal. That's why the mode looks like that, the electric field. Yes?
So is it alternating between positive and negative maximums? Like it's not just 0 to positive, it's going negative too.
It's this thing that does that, right? Because cosine of 0, so in time, cosine of 0. Remember what I said, when you solve the time harmonic Maxwell's equations, you get a picture of the electric field, like kind of frozen in time. And then you add this e to the j omega t real part, and every single vector in that picture oscillates with a time harmonic, right? Harmonically, sinusoidally. So that's why this mode looks like this, right? It's maximum halfway along the x-axis and maximum halfway along the z-axis, so it's a maximum in the center, yeah? All right, that's one thing, one observation. Let's look at the magnetic field now. The magnetic field, first thing I want to point out is look at the energy inside of this cavity, right? Remember, what is the energy? The electric energy is the volume integral of magnitude E squared times epsilon over 4, right? So when is the electric energy maximum? At that point. At that point, it's a positive maxima. Okay, so you get, it's at magnitude squared, so you get absolute value. But the electric field vectors are pointing vertically, then down, then up, then down because of this cosine omega t. But in either case, you're going to take the magnitude, you're going to square that, so you'll get the same energy when it's pointed up and when it's pointed down, right? But you get a maximum there and a maximum there, and you get 0 there, right? There's a point where there's no electric energy. But notice that the magnetic field, all the energy in the electric field oscillated into the magnetic field. What is this? It's a resonator, right? Have you guys heard of a tank circuit where you have an inductor in parallel with a capacitor, and you feed them both, right? How does that work? All the energy goes in the capacitor, and then it ends up dissipating into the inductor, and then it ends up dissipating back into the capacitor. So what's happening here is the energy is sloshing back and forth between the inductor and the capacitor, or in this case, between the electric field and the magnetic field. So it's like a slinky, if you will. So good. So whenever the electric field is 0, the magnetic field is maximum, and whenever the magnetic field is maximum, the electric field is 0. Okay, so what does that imply? That implies that the electric field is, I wouldn't say, maybe it's orthogonal, I wouldn't say that though. It's out of phase, it's 90 degrees out of phase, right? 90 degrees out of phase. We should see that in the mathematics. So here we have EY 101. This is completely real, right? There's no imaginary numbers in this entire expression. Remember, beta x is pi x over a, right? Now, this expression for hx has a j in front of it, but everything else is real. And a j is a 90-degree phase delay, right? Same with this one. hz has a 90-degree phase delay. Good. All right. So that's what I wanted to talk about with this. So this is the dominant mode, and the energy is just exchanging between the electric and magnetic fields, right? So what is this? How do we get this expression here? We should have, so the electric field is vertical in a TE to Z mode. The magnetic field circulates, right, in the XZ plane. So it's a rotating in the XZ plane in rings, closed loops. So here, this has an X and a Z component. And if you look at the way these are arranged, you'll see this expression, right? This expression has, so it's a maximum in the middle and 0 on the ends. So this has sinusoidal dependence, right? Just like this one does. Sinusoidal dependence in the X direction. So let's check that. In the X direction, we have sinusoidal dependence for the X component, right? On this face, it's purely an X component because it's a ring, a loop. Then it becomes purely a Z component here, right? Because it goes in a circle like this. So it goes like this. So here you have purely X, here you have purely Z, yeah? All right, so let's see. In the Z direction, we expect also sinusoidal, right? And we have that here for the Z component. Good. All right, very nice. Let's move on. TM to Z modes of a rectangular waveguide, same thing now, but we're going to derive the TM modes. So we start with the magnetic vector potential that has a Z component only. We borrowed the result that we derived for the waveguide, and now we bound the Z direction. So we have cosine and sine, right? And we have beta y and beta x the same as before. The new boundary condition is to apply on the front and back walls at Z equal to C and Z equal to 0, the EX and EY should be equal to 0, right? Yes, these are the tangential components, X and Y, in the Z direction. All right, good. So applying the boundary condition to EX, we calculate EX for the TM modes, and now we have to differentiate with respect to Z. So before, nothing really changed. When we changed the exponential for the waveguide solution in the Z direction to the sine and cosine for the standing wave in the Z direction for the cavity, we didn't have to worry about altering the expressions that much. But now we have to differentiate in the Z direction. So we get this cosine becomes minus sine, this sine becomes cosine, and we evaluate that at Z equal to 0. Okay, that gives us this, right? We need this to equal to 0. So there should be equal to 0 there. And that means that D3 has to be 0. Okay, now we apply the other boundary condition. We know that D3 is equal to 0, so this term goes away. And we evaluate this. This should be a C. This should be equal to 0 as well. And we get the eigenvalue in the Z direction. Right, it's the same one as the TE case. All right, good. Okay. All right, so here are all the expressions. We now have the correct A, which has cosine, sine, and sine. And we can find EX, EY, EZ, HX, HY, HZ, and we can find the resonant frequency from the separation equation. This comes from beta x squared, beta y squared, beta z squared equals to beta squared, beta naught squared, let's say. That is equal to omega. Let's call it beta r, right? I think that's because it's a resonant. We're looking for the particular eigenvalues that are resonant, right? Beta r squared, omega r squared mu epsilon, and then this is equal to 2 pi f r squared mu epsilon. And from there, you can get this expression, right? All right, good. The modal indices are different. Note, they used to start at 0, or 0 is included, or this is excluded. M equal to N equal to 0 is excluded, but that's already excluded in this set anyway. So neither of these can ever be 0. But before, they both couldn't be 0 simultaneous, but one could be and the other couldn't. All right, so you'll find the lowest order mode for TM is 110, and we'll see that. All right, good. So let's look at the mode order for the rectangular cavity. since the expressions for the resonant frequency of the TE-MNP and the TM-NNP modes is the same. I don't know if you noticed that, but these expressions are exactly identical. This expression for the TM and the TE one were exactly the same. The order in which the modes occur can be found by forming the ratio of the resonant frequency of any MNP mode, TE or TM, to that of the TE101 mode. So the strategy is this. We define this variable R, right? R is the ratio of the resonant frequency of the MNP mode, could be TE or TM, to that of the resonant frequency of the TE to Z101 mode. This is the first one that always occurs, the dominant, right? All right, so we know what the expression is for the resonant frequency MNP. It's either TE or TM, they're the exact same expressions. It's this, and then for the 101 mode, it's a square root of this, but since these are both square rooted, you can put the square root around everything, right? All right, so now, for different values of A, B, and C, so the A over B and C over B, we calculate what this R is, right? So for the TE101 mode, if we're looking for the TE101 mode and we ratio that to the resonant frequency of the TE101 mode, we should always get 1, right? The ratio should be 1. So this whole column is 1, R equal to 1. Now, the next mode, depending on what your configuration is, A over B and B over C, the next mode could be TE011, and the third mode is TM110, and so forth, right? And if you know the resonant frequency of your TE101 mode, then you can multiply by this factor, because if I want to find the resonant frequency of MNP, I can multiply both sides of this equality with the FR TE to Z101, multiply by the R, right? All right, good. So the waveguide we've been using for all these examples has this ratio. Oh my goodness. Oh no.
So as you change which side is rectangular, which side is square, would it really matter what the index ordering is?
Well, yeah, I mean, so the A is in the X, B is in the Y, C is in the Z for the configuration that we're studying. So that will, and then the mode configurations were TE to Z, TM to Z, so it does matter. Okay, so for the waveguide we've been using, A was 2.286 centimeter, B was 1.016 centimeter, and we're saying also that A is equal to C, or C is equal to A. So it's this row, right? This entire row right here is what we've been using in all of our examples we've been studying. So that means that the TM110 mode happens at 1.74 multiplied, or 1.74 times the resonant frequency of the TE101 mode. All right, so let's go verify that. All right. So here, the first TM mode is TM110 and occurs at 1.74 we got from the table, multiplied by the resonant frequency of the 101 mode, TE101 mode, which for our X-band waveguide example is, we calculated this before, 9.2726 gigahertz as FR101 TE to Z, and multiply that by 1.74. The first dominant TM mode should happen at 16.134 gigahertz. If you redo the CST eigenmode simulation, but now you increase the frequency range up to 20 gigahertz, because the first one I did was 5 to 15. Search for modes between 5 and 15. It didn't see this TM mode because it happens at 16 gigahertz. So I increased it to 20, and now it caught 5 modes instead of 3. And this happens at 16.144, which is close to what we expect, yeah? All right, good. So let's look at the modal profiles for the TM110 mode. Here's EZ, here's HX and HY. All right. Transverse magnetic to Z means that there is no HZ. We have that, right? But there is an EZ now. All right. Okay, so this one, let's try to understand this. Same thing here. We have the electric field peaks when the magnetic field is 0, and vice versa. Are these out of sync or what? This one's going to 360. They're almost in phase, right? It looks kind of out of phase. All right, but anyway, let's take a look at this, EZ. So this is always pointing in the Z direction, always, right? This is forming a closed loop. in the z x plane. No. I take that back. There is no, is there no x component? Let me go check. Sorry. EX for 110. So 110 means that there should be an x component, right?
Order for beat base.
Oh yeah, this all goes to 0, so it kills the x component. All right. Okay, so that means that this electric field is always into the board, yeah? No, it's not letting me erase anything. That's kind of... Okay. Let me see if I can... Sorry. Let me get out of this and discard and play from current. Okay, so what? Oh, the electric field's always in the z direction, right? Which is this way. Fine. It has sinusoidal dependence in x, so 0, maximum 0. That makes sense. Sinusoidal dependence in y, 0, maximum 0. That's why the maximum is here in the center of this cross-section, xy plane, right? And in the z direction, it's constant. So this looks like a, like a cylinder. Okay, here, the magnetic field now forms loops in the xy plane, right? These should be out of phase. We have a J over here. We have no J on either of these terms, right? So they're 90 degrees out of phase. And we have sinusoidal for the x component. The x-axis is this way. So the x component, we have sinusoidal in x, 0, maximum 0, makes sense. But we have cosinusoid in the y. So we have max, 0, max. So you get this kind of field profile, yeah? And again, no z dependence. It's kind of a funny mode. TM. All right. Okay, good. Very nice. All right. So we have one more topic to study today, and it's a very, very, very important topic. All right. This is something I really want you to pay attention to understand. This is called the transverse resonance method. And in a lot of waveguide problems, the first thing you need to do for any transmission line, any waveguide, you need to know 3 parameters. You need to know beta, alpha, and the wave impedance, right? Or the input impedance, so that you can match to it, launch things into it, and you want to be able to calculate what the phase delay is across a given length of line and the loss across a given length of line. You need those 3 parameters, right? And then you also kind of want to know what the field looks like, so you might need to calculate E and H. All right, but this approach, transverse resonance, gives you the wave numbers fast, alpha and beta. Way better or way faster than any other approach. But that's all it gives you. It won't tell you what the mode looks like. It won't tell you what the electric and magnetic field look like. And it will not tell you what the wave impedance is, or the characteristic impedance, or the input impedance, any of that, right? It will only tell you alpha and beta. But it's super powerful to know those numbers, right? Okay, so let's first to study the transverse resonance method, we need to revisit the directional wave impedances we studied last semester, all right? And this is a slide, a repeat. Some of this is a repeat from last semester slide. A plane wave mode, which is TEM, transverse electric and magnetic, to the direction of travel, will have the same wave impedance in the direction of beta equal to the intrinsic impedance of the medium. What am I saying there? I'm saying that E divided by H, which is E and H are orthogonal to the direction of propagation because it's a TEM mode. If I calculate the wave impedance, which has the orthogonal components to the direction of propagation, then I get the square root of mu over epsilon is the same thing, right? It's equal to the intrinsic impedance of the medium because it's a TEM mode. All right? Now, there are other directional impedances that we can calculate toward the X and Z directions, and they can also be defined, right? For obliquely traveling plane waves, this might make sense, because this plane wave traveling oblique with respect to the coordinate axis of which we're going to decompose the electric fields into, and magnetic fields. These impedances are obtained by dividing the electric field component by the corresponding orthogonal magnetic field component. And these 2 components are chosen such that their cross product gives the direction of power flow. So let's look at it. TE to Y modes, right? What does TE to Y mean? Means that the electric field is orthogonal to Y. So that's this picture. The electric, here's the y-axis coming out of the board. The electric field is in the plane of the board. So it's orthogonal to y. This is a TE to y plane wave. All right, good. Now we can define a wave impedance with either E crossed with H. So here's, this picture shows both a forward traveling wave and a backward traveling wave, all right, in both one figure. So don't get confused. This is kind of two different things. There's a plus, everything's plus over here, traveling that way. Everything's minus, superscript minus, traveling that way. All right, let's look at the plus traveling wave. If I take E cross with H, I get the direction of propagation. That wave impedance, the full E over the full H, is equal to the intrinsic impedance of the medium because that's a TEM mode. If I calculate the impedance with respect to the direction of propagation, which is beta. I can also decompose E into an EX and an EZ when it's traveling obliquely to this XYZ coordinate system. Those components, I can then form new impedances with EZ over H and EX over H. Those are called directional wave impedances. They're very useful, very, very useful. So it's something you should really pay attention to. All right? So, because you can draw transmission line analogies using these directional wave impedances and solve reflection problems on multi-layered planar stratified media and things like that much, much easier. So, ZX then, let's look at what ZX is. For the forward traveling wave, we're saying it's going to be minus, we'll see why there's a minus sign, EZ plus over HY plus, right? So EZ plus is this component, and HY is, HH is all the way in the Y direction, right? So EX, EX is, EZ is this way, right? So the Z-axis is that way, but this is minus EZ. So if I take minus EZ, which is this way, and I cross it with H, so that way, right? That way is minus EZ, and I cross it with H, then my thumb points vertically, and that is one of the components in the direction of travel. There's a vertical component to this direction of travel and a horizontal. Here it is, beta X and beta Z, all right? So why do I have to include this minus sign? Because if it was just EZ over HY, then I would have EZ like this, that, HY, and then I would point down, and that is not one of the components in the direction of direction of travel. All right, now let's look at this. What is EZ over HY, right? EZ is what? Okay, so EZ over HY, right? So we know that Z is normally, let's say EZ over HY and a minus sign, right? EZ is what? EZ is going to be this component of this triangle, which is going to be the sine, right? So EZ is E times the sine of theta incidence, right? From trigonometry. And then we divide by HY, but HY is all of H, right? So I should be putting magnitudes on these because they're to be correct. So then that's nothing but magnitude of E divided by magnitude of H multiplied by the sine of theta I. And we know magnitude of E over magnitude of H is equal to eta. So it's eta times sine of theta I, right? Okay, good. Now, okay, the next thing is, let's calculate ZX minus for the minus traveling wave. The minus traveling wave is EZ minus over HY minus. Why? Because EZ minus is that way, right? Yeah, EZ minus is that way. And we rotate to H, which is in the plane of the board. That gives me a component downward, and the direction of travel has a downward component and a leftward component. So that works. All right. Okay, let's now use this triangle here to calculate what that should be. So if we use this triangle here, it's the same thing, right? It's EZ minus divided by HY minus. Well, EZ minus is nothing but the sine of theta I times E times E. We divide that by H is all the way in that direction. But H is now minus Y, right? So, and then I think this one we need a minus sign because it's pointed along the minus Z. So those two minuses cancel. We get eta times sine of theta I. The conclusion that I need you to understand or draw is that the wave impedance for the forward traveling wave is equal to the wave impedance for the minus traveling wave. All right? Those wave impedances are equal. They're both eta sine theta I. Okay, good. Hold that thought. Let's look at solving this kind of problem here. we have a rectangular waveguide which is inhomogeneously filled. It has epsilon d mu d as a slab of permittivity epsilon d mu d that runs along the z-axis and fills the rectangular waveguide in the x direction and has a height h in the y direction. And then there's air above it, all right? You can model the transverse section of this waveguide using this. This is a transverse, a cross section, right? The transverse plane. What do I have here? A in the x direction, B in the y direction, H for the slab in the y direction, epsilon d mu d, epsilon naught mu naught, all right? And there's, okay, this is the cross section of the waveguide. You can model this using a transmission line model. So this is a transmission line, short on one end, short on the other end, and it has air above and dielectric below. All right, so it looks like this, right? This has this transmission line model, short circuit. Here you have, here you would have ZD. This would be a length H. Then you would have another piece of line here, which is of a height B minus H. And this one would have Z naught, and this will also be shorted. All right? That's this figure here. Okay, now, good. We showed previously that the wave impedances of the waves in the positive and negative directions are equal. That was key for how this works. But if you look back, the ratio, oh, I've repeated it here. The wave impedances are equal. They're both equal to sine eta times sine theta I. ZZ plus is equal to ZZ minus. Wave impedance in the direction of travel of this thing. In the direction of travel is the forward traveling wave impedance is the same as the negative traveling wave impedance, all right? But their components were, it's still EX over HY in both cases, but one of them has a minus sign. So that's critical, right? Now, what is EX over HY? That's nothing but the input impedance in the cross-section of the waveguide. This is a wave impedance in the direction of travel. The z-directed wave impedances are equal. Forward traveling and backward traveling equal. That means that EX plus over HY plus is equal to negative EX minus over HY minus. All right? Now, these are both the same thing, EX plus, HY plus. They're the fields in the cross-section of the waveguide, the transverse plane. Okay, these EX over HY are the characteristic impedances or the input impedances of the transmission line model that represents the transverse section of the waveguide. Let's read it. The ratios of the corresponding electric and magnetic field component magnitudes were equal, but opposite in direction. Okay, since the input impedance of a transmission line is defined as the ratio of the electric to magnetic field components or voltage to current, then at any point along the transverse direction of the waveguide structure, any point along the transverse direction of the waveguide structure, the input impedance of the transmission line network looking in the positive y direction, Z up, is equal in magnitude but opposite in phase to that looking in the negative y direction, or Z down. And it's all because the wave impedance of the forward traveling wave is the same as the negative traveling wave, but these are defined with a minus sign differently. So if we say EX plus over HY plus, we call that Z input up in the plus Y direction, and EX plus over HY, or EX minus over HY minus is Z in looking down. They have a minus sign difference, but that only comes because we can only equate these two expressions because the wave impedance direction of travel is the same. All right, so that means that the input impedance of the transverse line, this transverse line, Z looking up and Z looking down are equal and opposite in sign, right? That equation is super powerful. This also follows from the transverse cross section. Why we're looking at this, because EX and HY are, okay, so the boundary condition requires the continuous tangential components of electromagnetic fields at any plane orthogonal to the transverse of the structure, right? So the EX and HY are, let's see, EX is tangential to this transverse cross section, and HY is normal, but it's also, HY is normal, right? But EX matters. And HY, so this, the tangential field components have to be continuous at a plane orthogonal to the transverse structure, in and out of the board. All right, good. This is the key. How do we get to it? The direction, the wave impedances in the direction of travel are equal, but they're defined with the minus sign difference And they're also ratios of transverse field components to the direction of propagation. And since we have a transverse model of the waveguide, then these transverse component ratio is equal to the characteristic impedance or the input impedance of our transmission line, which models the transverse cross section of the waveguide in the direction of travel. All right, that's where this equation arises. It's super useful, this equation. All right, let's take a look. So the input impedance seen looking up to the airfield portion toward the shorted load, looking up, is Z in the plus Y direction is ZC naught, where ZC naught is the characteristic impedance of the airfield line multiplied by ZL plus JZ naught tan beta L, Z naught plus JZL tan beta L, right? Evaluated at ZL equals 0 because it's the cross section of a waveguide has short circuits on both top and bottom and the sides, right? But that gives us this, JZ naught tan beta L, right? These are very, you should probably have seen these before. The input impedance seen looking down into the dielectric field portion toward the shorted load is this, right? But now we have dielectric instead of ZC dielectric instead of ZC naught. And we have tangential beta dielectric instead of tangential beta naught for free space. Okay, note that the transverse beta squared is equal to beta x squared plus beta y squared. It's a transverse beta. Beta z is the axial beta or longitudinal beta. And beta transverse dielectric squared plus beta z squared, that's beta x squared plus beta y squared plus beta z squared now. All three of them, which means this is just beta naught or beta d in this case, right? Omega squared root of mu d epsilon d. Omega squared root of, or not square root, omega squared mu d epsilon d. And beta in the air region plus beta z squared is beta naught squared is omega squared mu naught epsilon naught. All right. Okay. By the transverse resonance method, these two impedances are equal and opposite. So ZC naught tan beta L is equal to minus ZCD tan beta TD. All right. This transverse resonance equation is applicable to both TE and TM modes. And we're going to use it to study the TE to Y modes next. So we're going to solve, this is the last slide. So previously we found that the wave impedance of the, okay, so back a few slides ago when we first started deriving, you know what, I don't want to rush through this. I feel like I'm talking too fast. I'm going to go through this. Let's save this for next lecture, yeah? It's super important. I want you to learn it. So, because we only have a minute left. So let's come back. Next time we'll start with transverse resonance again.
2 slides ago, Steve, things, can we use that to convert between beta and beta?
You convert between eta and beta. That's
Yeah, that one. Can we use that to convert, because we have beta cosine of theta I, but we know what beta is in the direction of travel. And can we use that to get the beta component of beta G and beta X based on?
Last time.
yeah. If you know theta, you can find beta x and beta z, right? Yeah, of course. Good. All right.
So in the partially filled waveguide,
No problem. Have a good one.
it's traveling in the Y direction. It's not traveling in the Z direction.
No, still traveling in the z direction.
Oh, but the electric field is now tangential to Y, not.
TE to Y modes. So that means the electric field is transverse to Y, means it could have an X and a Z component. It's a different mode, right? Yeah, it's a different mode set. It's not TE to Z anymore, it's TE to Y. That's probably why I wanted to come back to that and do it a little more slowly. I didn't even mention that. Good.
Yeah, I had a bunch of classes in the last semester where then they would like have the and
See you Monday.
like auto focusing where the students are, so I sit like really far.
Yeah, no problem. Have a good one.
You're like,
You too. See you guys.
I have another class here.
What's that?
I have another class.
Oh,
here.
serious?
Yeah.
There's
I
class
have
this
your
late?
class and then the other class all together.
What class is that late?
Digital signal processing.
Oh, I've never heard of classes that go that late.
Yeah.
That's cool. Very nice.
I don't have to change last. I don't have
Oh,
to
yeah,
change
very-
roads yet.
Very good. It said 15 minutes to run. Yeah, I don't know why it's only one.